Hello everyone! In this video, we will talk about how to efficiently model and analyze Slender structures. Slender structures are all around us and are very common in engineering design. From the buildings and bridges in our cities to the power transmission line towers that provide energy to them, to construction and transportation equipment that is used to build and supply them, and even your bicycle. While modern-day modeling and simulation tools like Ansys Discovery and Ansys Mechanical can construct and simulate these structures as solid bodies, representing them as line bodies or beam elements has distinct advantages. In this video, we will discuss when to use beam elements, what makes them unique, along with special considerations for their proper usage. Finally, we will review results that are specific to beam elements. We will do this via a short lecture and walk through an example of a utility trailer assembly. Let's get started. A question one may ask is, when do we use line bodies? When it comes to simulating slender structures like columns or beams, line bodies are often the best choice because of their computational efficiency. Take, for example, this large structure. We can see the construction is made of long, slender bodies or beams. When the length of the member is much larger than the cross-sectional dimension, a line body is well suited to model the behavior, but one can also use a more quantitative measure, which is the slenderness ratio. Slenderness ratio of a beam structure can be calculated as G times A times L squared over EI, where G is a shear modulus, A is cross-section area, L is the member length, not the individual element length, E is the Young's modulus, and I is the area moment of inertia. As a general guideline, a slenderness ratio greater than 30 is recommended for using line bodies. Here, we compare the slenderness ratio between two beams made of the same material to give a visual sense to the slenderness ratio. When deciding when to use a line body, it is important to understand how a beam responds to different loading conditions and what types of deformation we can expect. This way, we can decide whether it will meet our simulation needs. Let's have a look at the different modes of deformation are captured by a beam element. If we take the beam and apply an axial load, the beam will stretch or strain, and we will generate normal or axial stress acting along the length of the beam. Now let's take the same beam and put a moment load to bend it. We see that beam has curvature to it, and its curvature causes strains to develop through the cross-section that varies from the extreme fibers or top to bottom, if you will. But again, these strains and associated stresses are still acting in a normal or axial direction of the beam. If a torsion load is applied to the beam will twist and generate shear stresses. Here we can see one such example of the development of a shear stress from a torsional load. Keep in mind that the planar section of a beam remain planar, and deformations and stresses in the plane of the section are not considered as part of the formulation. So, while we can capture the overall response of a beam-like structure accurately with the beam elements, highly localized deformation can't be captured with the beam formulation. For such situations of very localized behavior, modeling the region of a structure with a solid model or considering using beam-to-solid submodeling approach. Now, another common question asked is why one should use line bodies. The line body offers us several distinct advantages comparing to solid or surface bodies. A point that we should remember is that when using a solid element, it's ideal to have an aspect ratio close to 1, although higher aspect ratios can be tolerated and it still yield useful results. However, in the case of slender structures, we may end up either with extremely high aspect ratio elements that act overly stiff and don't capture the deformation well, or we will end up with a very large number of elements that may have reasonable aspect ratios. Thus, by using line bodies when applicable, we end up with significantly fewer degrees of freedom while retaining higher accuracy. As an example, let's compare the number of degrees of freedom for this I-beam. If we mesh it with a line body, we can see we have significantly fewer degrees of freedom compared to the other element topologies, and this translates into faster solution times. Another big advantage to using line bodies is the direct output of commonly requested beam results, such as axial, bending, torsion, and shear forces and moments. In the case of slender structures, we are often interested in identifying and separating axial and bending behavior, for example, to determine how the slender structure is responding, and this is directly possible with line bodies because its formulation incorporates these modes of deformation. On the other hand, this would be very difficult or tedious to attempt with a solid mesh, which is intended for more general modes of deformation. The ability to easily modify a beam cross-section compared to the more time-consuming updates to a solid model geometry is a big advantage when performing design studies. Furthermore, making the changes to the section dimensions is updated everywhere the section profile is referenced, so a simple change can be reflected across a model with many beams. Now that we know when and why to use line bodies, we may ask what makes line bodies elements so unique. There are several model types of line body elements to represent specific structures. The beam model type is one of the most common and will be the type we cover in this video. Some other types are for more specialized cases, such as modeling piping, modeling truss-like structures which cannot transfer moment, modeling reinforcements such as rebar in concrete or corded reinforcements in rubber tires, modeling cables where the tensile-only behavior is required. While we will focus on beam elements, the discussions we have regarding modeling, orientation, and results generally still apply to other types of line body elements. Even though the line body is often an excellent choice for slender structures, there are few considerations to be aware of. The stress state is simplified for beam elements, and the kinematics that governs the beam behavior comes from beam theory, so line bodies should not be used for non-slender geometries since we have only 3 stress terms. Shells or solids would be better suited in these cases. Also, detailed stress at the beam-to-beam intersections, weldments, bolt attachments, holes are not accounted for, so for detailed design, a local shell or solid model may be required, or even the sub-modeling technique may be used. While the beam element is 1D, the cross-sectional information is stored and calculated to allow for 3D visualization, greatly facilitating results interpretation. Keep in mind that we can represent the beam behavior with just a single element, but adding more nodes along the length may be necessary or desirable if we wish to more accurately visualize results along the beam. For example, with a shear moment diagram or results at a specific location along the beam. We may also need more elements to interface with other parts at specific location, or even where point loads and moments will be specified. Lastly, beam can be offset from their geometric modeling line bodies to occupy a different location in space to capture proper stiffness while facilitating connecting to other bodies. We will see an example of this in the walkthrough portion of the lesson. One other important consideration is that beam elements have their element coordinate system oriented with X along the axis of a beam, and then Y and Z in plane. This can be important to properly orient the beam section, and it's also important when extracting results since the stress-strain results will be reported in this element coordinate system. This brings us to our final discussion on the results obtained from the beam elements. There are several types of results available with the beam elements. The forces and moments available in beam results, including the popular shear moment diagram. There is a direct stress, which is the normal stress from the axial loading on the beam, and combined stress, which is the normal stress from the axial loading plus the normal stress from bending. The beam section results are also available, which enables us to visualize the stresses and strains using the same results quantities as with the other element topologies such as shells and solids. Keep in mind these quantities are in element coordinate system as previously mentioned. As a side note, these beam section results allow us to visualize more advanced quantities such as the nonlinear results like plastic strain, for example. Let's set up a simulation of a trailer for a better understanding of the line body usage. We will use the simplified trailer 3D model as the basis for beam model. The wheels and tires will not be needed, neither will the hitch jack. These components will be excluded from the simulation. Looking ahead to the finite element model, we need to connect the frame to the axle, and we will do so with springs. To create the spring locations, the two side rails will be split by these planes. The axle will be split at the out faces of the two side rails. We will fix one side at the hitch jack location, given that jack is down. This hitch beam will be split by this plane. The Ansys model that we are providing for the walkthrough example will already have the wheels and the hitch jack excluded and beams split at the specific locations, and it looks like this. Let's get started. Insert static structural system to the project page. Import the geometry. Right-click on the geometry cell and choose Edit Geometry in Discovery. The geometry consists of the solid bodies. However, we would like to simplify the model by using the line bodies to create a more efficient model for the analysis. We can extract the beam representation of the solid bodies in Discovery. Go to the Prepare tab, Beams and Shells Extract. Select this first beam. The extracted beam is seen in the tree. If we go to Physics, right-click on Extracted Beam 1 and choose Edit, we can click on Profile Properties to see the geometrical properties of the extracted beam profile. Repeat this process for the rest of the beams. All the beams with the same cross-section are grouped under the single extracted beam under the tree, since a single cross-section profile is sufficient to describe all such beams. Both standard and non-standard beam cross-sections can be extracted by Discovery. Next, we need to move the hitch beams to be in the same plane as the frame beams to create the shared topology between them. This will create shared nodes where the hitch beams and frame beams intersect once we mesh the model in Mechanical. Click on the Design tab, choose the Move tool, and select the three hitch beams. Use Up to tool to select the first cross beam. This should put the hitch beams and the frame beams in the same plane. Go to Prepare tab, Share Topology, Share. Discovery automatically finds the locations where the beams intersect each other. Click on the green check mark to accept the operation and create shared points between intersected beams. Now the geometry is ready for Mechanical. Click on the model in the static structural template on the project page to open Mechanical. We have brought the line bodies in Mechanical. Click Display and Cross-Section to visualize the cross-section of the beams. The hitch beams and the frame beams are in the same plane and intersecting each other as expected. However, we would like to represent the location of the beam where it should be in the physical space underneath the frame by offsetting the hinge beams 2 inches down from the frame. Expand the geometry, turn off the cross-section for better visualization of the line bodies. Select the hinge beams in the tree. In the details view, change the offset type to user-defined and set the offset to -2 inches. The FEA model will still be connected to the rest of the frame, while the beam representation shows that the hinge is properly offset below the frame. This offset is properly accounted for in the beam numerical formulation. Next, select all the beams in the tree and in the details view define material assignment to aluminum alloy. Now we would need to connect the frame and the axle with the springs. Turn off the cross-section by clicking on the cross-section and click on Show Vertices to easily select vertices that are going to be connected with the springs. Right mouse click on Connections and insert spring. In the details view, specify longitudinal stiffness 1000 pounds per inch and select the vertices by defining the scope under Reference and Mobile in the details view, creating the spring connection between the frame and the axle. Applied by should be set to direct attachment. Repeat these steps 3 times to create the rest of the springs between the axle and the frame. Let's mesh the model. Select Mesh and set up sizing resolution to 6. Right mouse click on Mesh and generate mesh. Turn off thick shells and beams. Under Display, select Preferences and check the node numbering. Zoom in the connection points and see that nodes are shared between hinge and the frame at the intersection. Uncheck the node numbers under Preferences. Next, we will create the path that will be used as a scope for the shear moment diagram once the model is solved. Right mouse click on Model, insert Construction Geometry Path. In the Details view, change Path Type to Edge. Set the selection filter to Edge and select these 9 beams that represent the entire side channel of the trailer. As a note, the path can contain beams of different cross-sections. Boundary conditions. Select the point that represents the jack stand. The point is halfway between the hinge intersection and where the hinge intersects the frame. Highlight static structural in the tree, insert displacement and specify 0 displacement for all 3 translation degrees of freedom. Select the vertex again, insert fixed rotation and free the rotation in the X and Z directions, leaving the rotation fixed in Y to prevent rotation of the trailer in the plane of the trailer. Since the axle is connected to the frame with just springs, in this demo example, it is not very stable in the global X direction as the springs lie in a common plane. In an actual design, there would be hardware to prevent this motion, so to prevent this lateral motion of the axle, we will fix one side of the axle in X. Select the vertex on one end of the axle and insert displacement and specify 0 displacement for X. Now, to simulate the wheel that would prevent motion of the axle in the vertical direction, we will fix the vertex in the Y direction. Specify 0 for Y. Since the translational springs connect to the axle to a point, they cannot resist rotation of the axle about its axis, so we will fix the vertex in the rotation X direction to prevent the axle from spinning. Select the vertex again, insert fixed rotation and free the rotation in Y and Z, leaving it fixed in rotation X. On the opposite side of the axle, we need to simulate the other wheel that would prevent motion of the axle in the vertical direction, so we will fix the vertex in the Y direction. Select the vertex and insert displacement and specify 0 displacement for Y. Next, insert line pressure. In the Details view under Geometry, select and apply on 21 edges as shown here. set defined by two components, and set y component to -2 pounds per inch. This line pressure represents the load the utility trailer will carry. For this demonstration, we have assumed the line pressure to be uniform, but in an actual design, the line pressure would typically vary based on the intended purpose and loads expected on the different members of the trailer. Next, insert gravity and define negative y direction to account for the self-weight of the trailer. Now we are ready to solve. Right mouse click on Solution and Solve. Let's post-process the results. Right mouse click on the solution and insert beam result, shear moment diagram. Choose the path that we previously created. Evaluate the results. The plots show the variation of the shears and moments in the side channel beam of the trailer and are useful in determining the type and size of the beam member to properly support the necessary loads without failure. If you switch to worksheet view, you can see shear moment diagram. We can also post-process a typical result such as total deformation by insert total deformation and evaluate the results. Animating the results, we can see the deformation shape and contours, but also notice how the springs are compressing under the specified loading as expected. Another beam-specific result is the beam tool. Select all the bodies except axle and evaluate. We can see the direct stress, which is the linearized stress result, defined simply as axial force in the beam divided by the cross-sectional area of the beam. We can also see the minimum and maximum combined stress, which is defined as direct stress plus minimum or maximum bending stress in the beams. While we can post-process direct and combined stress, we can also post-process the beam-specific result quantities, which enables us to visualize the stress and strain using the same result quantities as with other element topologies, such as shells and solids. Highlight the solution and in the Details view set the beam section results to yes, insert stress, normal, set the coordinate system to solution coordinate system. Stress is in x direction. Evaluate the results. Note that each beam element has the local x-axis along the direction of the beam. So let's summarize. Line bodies are an efficient way to model slender structures. The creation of line bodies using extraction from the solid model inside Ansys Discovery is a time-saving technique to build and connect the line body models. The line bodies are easily visualized with their 3D cross-sections, useful both for verifying the beam orientation as well as results evaluation. Beam sections are easily specified and modified, allowing for quick design changes. We discussed that beam elements are the most common line body type, with detailed results available from the forces and moments to more detailed stresses and strains. Connecting the line bodies to other regions of the model is possible, and we showed some simple examples. Finally, while line bodies work very well in many cases, understanding their limitations is important for proper usage. I hope you have found this video informative. Thank you for watching, and do visit our channel to discover more useful learning resources.